Hello, this is Mrs. Taylor, and I'm going to show you how we can use calculus to analyze horizontal and vertical motion. To start with, let's look at particle motion. So for whatever reason in calculus, we study the motion of a particle a lot. And we say particle, but really it can be any moving body. And typically it's either being thrown through the air, so that's vertical motion, or dropped off a cliff, that's vertical motion, or you have some particle that's moving horizontally, left to right. So here I have my little particle and he moves left to right. And so what we would do is we would track his position left and right, and then when you plot those points on a graph, your independent variable would be time. So at what time is he at what position? So you have t, which is time. And then you also have position, which is a function of time, so s of t. And so when you plot points, you don't get a straight line. Your line can actually become a curve, because if you think about it, as my particle moves, his position is increasing, but if he moves backwards, his position is decreasing. And so you could have a curve that goes up and then back down. So if derivatives represent rate of change, then if I take the derivative of my position function, I would get the rate of change of position, which is what we refer to as velocity, which is rate of change of position. And usually we don't write s of t. Typically we write v of t. Excuse me, not s prime of t, but v of t. But both indicate velocity. And if you think through it, if my rate of change is represented by velocity, then velocity represents speed. However, velocity can be positive or negative, because the positive or negative sign of velocity is telling you if position is increasing or decreasing. So not only does velocity give us speed, but it also gives us direction, because think about it, if position's increasing, it's moving to the right. If position's decreasing, it's moving to the left. So velocity, the number represents the speed, and the sign represents direction. If it's a horizontal motion, the direction is left and right. If it is a vertical motion, the direction is up and down. So if I take the derivative of velocity, what I get in that case is acceleration. So the rate of change of your velocity, which would be the rate of change of your speed. So that typically is how fast or how slow your body is changing in speed. So in an instant, we have speed, but the rate of change of that speed is acceleration. I think I just talked in circles. So we usually don't put s prime of, or double prime of t. Acceleration is a of t. And we like to think of acceleration as not just a number, but it also can be positive or negative. So it gives you the numerical acceleration, but it also gives you a direction. So when I am given a negative acceleration, it doesn't mean that it's decelerating or slowing down. It just means that your accelerating force is moving in a direction. So let me give you an example. If acceleration is negative, and that means that the accelerating force is moving, in this case, in a horizontal motion, that means the accelerating force is moving to the left. And if velocity is negative, that means that the speed and direction is to the left. So when acceleration is negative, we have this accelerant force pushing to the left. Velocity is negative, so the body's already moving to the left. So that means the body is actually speeding up because the accelerating force and the velocity are moving in the same direction. However, if let's say our particle is moving to the right, which would make velocity positive, but our accelerating force was moving to the left, then there's a force working against this body moving to the right. And so what that does is slow it down. So the bottom line here is that if velocity and acceleration are both positive or both negative, my moving body is speeding up. But if velocity and acceleration have opposite signs, my moving body is slowing down. And so there's just a really quick overview of the relationship between position, velocity, and acceleration. When you move into problems involving horizontal and vertical motion, you're going to get into a lot of vocabulary, and you need to fully understand what the vocabulary means. And so some key words that you're going to see are displacement, position, velocity, speed, average velocity, and acceleration. And so what I'm going to do is I'm just going to use this video to give you some information about each of these words and what connections you're supposed to make when you see them. So we'll start with displacement. Displacement is the distance from a starting point. So after an interval of time, when your body maybe comes to a stop, how far is it from where it started? And we can represent displacement as delta S. Remember, delta in math means change. And so this is the change in S, which represents position. So it literally translates to change in position. So how far did you change from your starting to your ending? And so what this equals is S of t plus delta t minus S of t. So if t is your time when you start, and delta t is the amount of time that passed between your starting and when you want to know the displacement, then t plus delta t just represents the time at the end of the interval. So if you start at 0 and you go for a minute, then 0 plus that minute would be 1. So this would be S of 1 minus S of 0. And all that really means is you take your finishing position and subtract your starting position. And so if you think through it, remember when we're graphing a horizontal motion, your initial position will be an x value, your final position will be an x value on this horizontal number line. And so when you subtract the two, you get the distance from where you started. So just to break down this formula, I've labeled what each of these terms means. Delta S is your change in position, S of t plus delta t is the position at the end of the interval, and S of t is the initial position. So all this talk about position, let's move on to what exactly position means in the context of a problem. Position is represented as S of t, and it is the location of whatever your moving body is at an instant. So it's in terms of time. S of t, t is time. So it's dependent upon a time, an instant. So it gives you whatever the location is at a instant in time. 2 seconds, where's the position? 3 seconds, where's the position? It means you would plug 2 in to your position function for t, and it gives you the position at that exact instant. Really, that's about all you can say about position. Next one is velocity. And we have already established that velocity is s prime of t, or v of t. It represents speed and direction. So the numerical value is your speed, and then the sign is your direction. And just more information about the direction and what that means. If we have horizontal motion, then velocity's negative value would be moving to the left, positive would be to the right. If it's vertical motion, negative would be moving down and positive would be moving up. And so if I wanted the speed, what I would do is find the absolute value of velocity. And so you need to be really careful with this concept of velocity having two different meanings, because if the question you're given is free response and you were to be asked the speed and you did not remove a negative symbol from your answer, you would not receive credit because speed cannot be negative. And so you would have to communicate that you understood that the negative was direction and did not have anything to do with the speed of your moving body. So then from speed, let's jump to average velocity. Average velocity occurs over an interval. So when I say velocity, or when you read velocity in a question, what they're asking for is instantaneous velocity. So they'll give you a time. They'll say, what was the velocity at 2 seconds? And so that means instantaneously, at those 2 seconds, what's the velocity at that instant? Average velocity would be over an interval. So they would say, what is the average velocity between 1 second and 5 seconds? And so if you're given an interval, use average velocity. If they just say velocity, it's instantaneous, and you use S prime of t. And they give you a closed interval, a to b. And so what you would do is average velocity is like finding the average rate of change, in other words, the slope of the secant line. So it's your slope formula, y2 minus y1 over x2 minus x1. But of course, you know, we use more mathy notation than that, so we use function notation, usually when we write the average velocity formula. And so it would look like this, S of B minus S of A over B minus A. Now here's the tricky part that people forget. Average velocity, you use the position function to find. Velocity, you take the derivative, plug in a t-value. But average velocity, you use position and plug in your A and B values, the endpoints of your interval. So it's really, really important that you remember that distinction. It happens a lot that students use the velocity function in this setup where they do V of B minus V of A, and that's incorrect because that's not finding average velocity. Just like if we're finding an average rate of change over an interval, we don't find the derivative and then use that, we use the original function. And another way to think of average velocity is displacement over change in time. So displacement would just be S of B minus S of A, the difference of your y values on the interval, over the change in time, which is just the difference of A and B, which represent your beginning time and ending time. So our last vocabulary word that we need to go over is acceleration. And acceleration is the rate of change of velocity. And we also know from the previous slide that it is the second derivative of position, so S double prime of t. It's the first derivative of velocity, so F prime of t. And then the short notation for acceleration is just A of t. So all three of those types of notation represent acceleration. And not only is it the rate of change of velocity, but it's also directional. So it's the same as with velocity, where if it's positive, it's moving up or right, and if it's negative, it's moving down or left. So think of acceleration as a force. So your accelerating force is moving up, down, left, or right. An example would be gravity is an accelerating force, pushing down. The other thing to remember about acceleration is when you are trying to determine if a moving body is speeding up or slowing down, you aren't looking to see if acceleration is positive or negative. You're actually looking at the sign of both acceleration and velocity. So just an aside to keep in mind is if you are trying to find when the moving body is speeding up, both acceleration and velocity have the same sign. And if you are looking at slowing down, acceleration and velocity have opposite signs. Because if you think of acceleration as more of a force, then it has to work with velocity in order for your moving body to speed up. And so this is just a one-shot picture at the things you need to know about horizontal and vertical motion, the various vocabulary words, and what you're supposed to interpret from the use of those words. What I have here is an example of applying this information. A dynamite blast propels a heavy rock straight up with a launch of 160 feet per second, which is about 109 miles per hour. We don't have a figure here. I borrowed this problem from a calculus textbook from Finney, Demena, and Waits. In the rest of the question, it says it reaches a height of s equals 160 t minus 16 t squared feet after t seconds. And so there's several questions here. A asks how high does the rock go? So what you would do is use the position function and find the maximum. B, what is the velocity and speed of the rock when it is 256 feet above the ground on the way up and on the way down? So they want to know velocity and speed, but they give you a height. So what you would do is you would take your position function, set it equal to this height, and solve for t to find the time when it's at this height. And you should get two values, when it reaches the height on the way up and when it reaches the height on the way down. After you get that time, you plug it into the velocity by taking the derivative of the position, and then you get your two values for velocity at that time. The answer you get when you plug it in, that's your velocity, and then you take the absolute value to find the speed. C, what is the acceleration of the rock at any time, t, during its flight after the blast? So to find acceleration at any time, you would find the second derivative of position. And then D, when does the rock hit the ground? Well, that's when height is 0. So you set your position function equal to 0, and then you solve. You should get two values, but one shouldn't make sense because your rock is starting at t equals 0, and so your position at the start should be 0. And so either your one solution will be 0, and it should because there's a t in both these terms. So I guess both your solutions will make sense, but one of the solutions will not make sense in the context of the question, which is when does it hit the ground. It wouldn't be at t equals 0 because that's when it started. So it's the second value when you solve. So that's just a really quick run through of how you would work these problems, how you apply what I just showed you to the problems. This is where we will start in class on Monday.